Welcome to our set of lecture videos for Astronomy Online. If you want to follow along the slides or print them out, there'll be a PDF on Blackboard for everything that we see. Throughout the videos, there will be lots of times where I suggest that you pause the video to think about a particular question or try to answer a multiple choice question to see if you're getting everything on the very first go. If you miss these sorts of questions, it's not a big deal, but it is something you'll want to take note of so that you can go back and review those topics that aren't quite clicking the first time. We're going to start with Chapter 1 in this video, and in the first week we'll see a lot of the first couple of chapters where we see the foundations of modern astronomy. So this very first slide, if you go to the PDF, it's actually a set of links to the textbook. So the nature of astronomy is just an introduction to what astronomy is. It's a very short section of Chapter 1. The ones in bold here are the ones that we're going to be focusing on in this particular lecture video, but we will want to review that whole first chapter. It's pretty short and it's good to read through. So the nature of astronomy can really be boiled down into what's on this slide, and you can read it on your own. I don't want to read the slides word for word. But one of the key things is that astronomy and science in general isn't this warehouse of stored knowledge. It's really a method of gathering new information. And a lot of the things that we're going to see in this semester will be understandings that we currently have. A lot of it will be sort of facts that have been around for hundreds of years, and so we're pretty confident on those. But there will be topics that we cover that are speculative or on the edge of our understanding that may change over the next couple of decades. Now, there's a couple of key terms that we want to get out of this first chapter. One is that when you have science, the way it works is you run experiments or you make observations, and with astronomy we have to rely on observations quite a bit because things that we study are so far away. But when we make these observations, we then want to come up with an idea for what physics or what understanding we can make that fit these observations, sort of a mathematical understanding that fits the observations that we have. When we come up with some model that is testable, so we can put this idea out there and somebody else can run some experiment or make some observations that test our idea, we can call that a hypothesis, and then we really get into what science is. And then the other key part of science is what we really mean when we talk about proving something true or false. So throughout the semester, we're going to have these questions that come up. This is our very first one. And what I want you to do is, once I go through the question and the options, and I will read through these slides so that we can really make sure we have this both in audio and in text, I want you to pause the video and actually write down your guess for these. I'll go through them right afterwards, but it's a really, really useful learning technique to sort of force yourself to commit to an answer. No one's going to be checking this. There's no stress or stakes involved. But seeing for yourself whether things are clicking the very first time, or if you have some background knowledge from some other class or something else that will help you with these topics. There will be several times where these questions come up before we've covered something, and that's to see if we have that understanding beforehand from some other source. So don't feel like you should be getting every single one of these questions right the first time through. Okay. So how many observational or experimental tests does it take to prove a hypothesis false? So does it take 0 and we can just call it false? Does it take 1 perfect test to prove it false? Does it take at least 3 to confirm your findings to prove a hypothesis false? Or would it take an infinite number of tests to prove a hypothesis false? So pause the video here and think about your answer for this. Okay, so for this one, if we wanted to prove a hypothesis false, it would just take one single test to do that. Let's imagine for a second, and this is a this is an idea in the book as well. Let's imagine for a second that we're on some island that has sheep on it, but all of the sheep on this island have black wool. So maybe we've observed all of these sheep around us, and our hypothesis is that all sheep have black wool. With that hypothesis, we would only need to find a single sheep, whether it's on our island or somewhere else, that has white wool, and then that would prove our hypothesis false. And we would have to alter our hypothesis, and then we could say most sheep have black wool. But our original statement would be wrong with that perfect observation or experiment. So science, a big chunk of science, is constantly testing hypotheses to be able to weed out the ones that are false. All right, this next question, though, is a little bit different. How many observational or experimental tests does it take to prove a hypothesis true? The options are the same: 0, 1, at least 3, or an infinite number. And again, I want you to pause the video and think about your guess before you move on, and we'll go through the answer. Okay, so let's go back to our sheep example. So now we've seen a couple of sheep maybe that have white wool. And so our hypothesis is that most sheep have white wool. At some point we've gotten to main continents, we've realized that sheep with black wool are actually fairly uncommon. But in order to prove our hypothesis true, whatever final decision that we come up with how we want to phrase that idea, in order to prove it 100% true, we would have to find every single sheep in the entire universe. It would take an infinite number of observations or tests to prove it 100% true. Now, of course, we can prove it true beyond a reasonable doubt, and that's a big distinction that we want to make in science. We can never prove something absolutely unquestionably true, but we can prove it true beyond a reasonable doubt. So the answer here for this 100% true kind of thought is an infinite number. Now, we have a word for once we have enough observations and tests that have proven our hypothesis true beyond a reasonable doubt. We've gathered all of these different observations that support our idea, and none of them have proven it false. Because remember, if we've got one test that proves it false, we have to change our hypothesis or throw it out. So once we've built up this huge amount of support, amount of observations and experiments for an idea, then that's finally when we get to call it a theory. The theory of gravity, the theory of evolution, the theory of climate change. These are all scientific ideas that have gathered so much information and so much support and so many experiments and observations that we really can trust them beyond a reasonable doubt, which is the best thing that science can do. Anytime a new idea comes out in science, there are plenty of other scientists that are trying to prove it false. There's really not this active, we all want to just support things and just assume that they're true. It's always trying to rigorously test any idea that comes out so that we can keep the strong ideas that are true beyond a reasonable doubt, and we can throw out the ideas that just don't fit the observations. One of the other things that we really have to trust in is a kind of way that we can think about it in astronomy. One of the fundamental principles that just our entire field of science in astronomy is based on is that anything that we can test with experiments here on Earth, any of the physics that go on here on Earth, are also true elsewhere in the universe. We can't travel to all of these different places in the universe, but what we can do is figure out how the world around us works, how the space around us works, and then assume that we can just build models with that built-in assumption, which may or may not be true. But one of the principles we have to accept to be able to do this kind of science is that the physics that works near us works everywhere in the universe. And all of our observations have agreed with that principle. And so nothing has proven that wrong. And so it's something that we just have to keep in mind as we move forward in this semester. There will be a couple of ideas or models on how the world works that can be really succinctly put together in one equation. And so we will see those equations in this class. We won't do calculations with them, but it's important that we recognize that some of these basic physical laws that we can think of that describe how the universe works can be written like an equation, but we'll also describe how they work in words, what things go into those, and just the meaning, the overall meaning behind those equations. The other important thing when we're talking about numbers and calculations and equations is that any time in science that we have a measurement, it's not just a single number. There also has to be some unit attached to it to give that number meaning. So for example, my cat Penelope was 5.5 years old when I recorded this video. 5.5 is the number and years is the unit. She weighs 12 pounds. 12 is the number, pounds is the unit. And yesterday she chased 2 bugs around the house. 2 is the number, bugs is the unit. Bugs is that thing that gives it meaning. It doesn't have to be one of the standard scientific units to count for what we're talking about here, but it's giving that number to a meaning. Because without units, we can go back to those same examples. Some of them make sense, but some of them don't. My cat Penelope is 5.5. We do describe people's ages like that, right? My niece is 12, or my uncle is 47, was at some point. But we can also lose a little bit of meaning. If you knew that I had just gotten a kitten, maybe my cat Penelope was 5.5 months old. Without that unit, we can't be quite sure. She weighs 12. We really hope that it's 12 pounds and not 12 kilograms, because that would be an enormous cat. But again, there's some guessing that we can make if we don't have those units, but it's not clear without them. And then that last example, yesterday she chased 2. 2 what? It could be anything without that unit. She could have chased 2 toys, 2 fake mouse toys around the house. She could have chased 2 rabbits out in the backyard. Without that unit, we don't have that full information. So anytime that you're looking up some number, or if you're describing some number in any kind of assignment, make sure that you include the unit attached to it. There's another pause and think question type that we can have. It won't just be multiple choice throughout this semester. But what I want you to do right now is to take a moment. So once I'm done talking, you can pause the video and picture a cube in your head. So a cube is one of these 3-dimensional shapes where each side is a square. The cube has sides. Each one of those square sides are 8 something long. We had this piece of paper and the units just got scribbled out. We don't know how big it is. Now what I want you to do is to imagine some familiar object near your cube to try to give it a sense of scale. So pause the video, do that briefly, think about what object you chose and what that meant for the unit that you had to come up with for that 8 somethings long. All right, so we'll pause the video and think. All right. Now, there's a lot of different things that I hear from semester to semester. Some people think of a little coffee cup near their cube. Some people think of a basketball near their cube. Some people think a little bit bigger. So I had a friend of mine make these sketches for us. So maybe Penelope is holding a cube toy on her head. We could have a gentleman cube, so it's a little bit bigger. Maybe the cat cube was 8 centimeters on each side, and the gentleman cube is 8 inches on each side. We could get bigger, right? We could get the cube of great wonder, which is 8 yards on each side. Or we could get even bigger and a cube being hit towards the earth in a game of galactic billiards, and maybe it's 8,000 miles on each side. Without that unit, we could have any one of these 4 or whatever you came up with. It wouldn't be wrong because we have that unclear number, the 8 without a unit. So keep that in mind. That's one of the big things we want to take away from chapter 1, is the importance of attaching meaning to the numbers that we see. The other key thing that we want to make sure we understand is units have that inherent meaning. If you know something is 5 kilometers away and something else is 5 miles away, those are different distances, and that has some meaning. And if you have an understanding of kilometers to miles, You know that the one that with 5 miles is further away and the one with 5 kilometers is closer. So if you ever join a 5K race, that's a 5-kilometer race, it's about 3 miles long. So prepare for it appropriately. But in astronomy, we're going to see brand new units that we just don't see in everyday life. So just distances alone, we're going to see a whole wide range of units. We're going to see kilometers. That's the more scientific standard length unit that we see in different sciences. But with astronomy, because our distances are so large, we come up with different units to use as well. So within the solar system, something we'll see fairly often is what's called an astronomical unit. That's the distance between the sun and the earth, and we use it as sort of a measuring stick for the distances to different objects in our solar system. As we get to further and further away objects, we'll talk about light years. That's the distance that light travels in a year, and we'll talk about light speed when we get to chapter 5. And we'll even see parsecs. Once we get all the way out into chapter, I think it's 19, we'll learn about how we measure the distances to stars and why the unit of parsecs is actually more useful to astronomers in many ways than light years, even though they're similar units the same way that kilometers and miles are similar units. While we're on the subject of numbers, there's one last key piece we want to make sure that we sort of start the semester with on the same level. Scales in astronomy are so large that we have to use scientific notation when we write these numbers out, especially all throughout the textbook. So I want to make sure that we're all a little bit comfortable with scientific notation as a whole. And really what it is it just saves us time in writing things out. It saves us figuring out exactly how many zeros we have to write after that number. And it's the same way that we use words to describe these things, like trillion. So for example, on the slide, we have this number fully written out, 1 with 12 zeros after it. And the only way that we can really describe that is we could say it's a million. That would work. But we have this word trillion that allows us to very succinctly describe what that number is, 1 trillion. And in scientific notation, it's the same idea. Rather than saving us time in speaking, it saves us time in writing. And so it's 10 raised to the power of 12. So scientific notation is based on powers of 10. And it's also called orders of magnitude, so you might see either of those terms in the future. And there's a link here. It's a clickable link in the PDF version of these slides. And so if you have no prior use of scientific notation, which is totally fair and that's all right, we're not going to be actively using it in assignments, but we are going to be seeing it all throughout the textbook. So if you aren't familiar with scientific notation, you should click on that link. There's information about how it works, and there's a little self-quiz that you can do to see if you can go between regular numbers and scientific notation or back again, so that we have a sense of what that actually means when we see that 10 to the 12 number in our textbooks. There's a video that I'd like you to watch that we'll be able to link in Blackboard, but we can also play it here right now. There's no spoken audio, so I'll just describe what we're seeing as we go through, but you can watch it on your own by clicking on the link either in the PDF version of the slides or on Blackboard. But what we're doing is we're going further and further away from Earth, and each couple of seconds, if we look at the very bottom of the screen, there's a scale that's being shown, and it's getting larger by a factor of 10 every single couple of seconds. So now we see the planet Earth, and now we're fully in the realm of astronomy. No other science deals with these scales that we're going to see from this point onwards. So we can see the Earth being part of the solar system now, and we'll learn all about the solar system in this class. As we get further and further away, we see the sort of outer reaches of what we call our solar system, the realm of things attached gravitationally to the sun. As we get further out, we start to see where nearby stars are in relation to us, and how all of these stars that we see as point sources in our night sky are part of a single galaxy, a sort of island of stars called the Milky Way galaxy in our case. But there are other galaxies out there, and so now we can start to see these different galaxies as we get further and further out. When we get to the largest scales, and we'll see this at the very end of the semester, we get this cosmic web where things are spread out in the universe, not perfectly symmetric everywhere, but actually in these little filament structures. We're zooming all the way back in because there's another piece of astronomy at the very smallest scales that we want to make sure that we recognize too. All right, so as we approach planet Earth, we're going to zoom in really close on this woman's eye, so just be aware of that. And then we'll get down to the smallest scales. So here we are, maybe in the realm of biology, right? The parts of the eye, we get into cellular structure. But as we get to even smaller scales, as we get into the very smallest scales in the physical world, we get back into the realm of astronomy. So here we are about to zoom in on atoms. So atoms and the electron clouds that go around them, and at the very core of those atoms, protons and neutrons. And the things that happen at the atomic level are really how we get so much information about stars from the light that they produce. And that will be something that we'll discuss in great detail in Chapter 5. So astronomy gets these very largest scales and also the very smallest scales. So again, you can look at that video again on your own on Blackboard or the link in the slides. Okay. Now, part of the first thing that I want you to do this week will be to read through the parts of Chapter 1 that we're skipping over and get through Chapter 2 as well. Chapter 2 is one of the most important parts of the first unit of chapters that we really talk about. And so the textbook's very readable compared to a lot of other textbooks. I quite like it. And it isn't something where I want you to read every single word on every single page, but just go through it and see what information is there. Anytime that you get to something in the slides that don't quite make sense, then it's useful to be able to know what additional information you can get from the textbook, as well as using the discussion boards or emailing me to be able to clarify things. You're not expected to understand everything in the textbook the very first time through. If you did, then there wouldn't be a reason for me to be here. But instead, it's actually shown through a lot of different scientific studies that if you see things in the textbook before you come across them in our discussions, either through these lecture videos or on the discussion boards, then things will actually click a little bit better when you go through them that second time through, having seen those terms and seen those images in the textbook the first time. Now, Chapter 1 ends with an understanding that not only does astronomy cover this vast range of size scales, but it also covers a vast range of time scales. So in this last portion of the chapter, one thing that the textbook does is bring the entire history of the universe and crush it down into one calendar year, one of our standard calendar years. Now, in this image that we see, January 1st, the very first second after we all celebrate New Year's, that's when the Big Bang occurs. We'll get to, at the very end of this semester, what the Big Bang is and what it isn't. There's a lot of misconceptions about that. But it is the starting moment in time for the universe. And then time continues forward, and all throughout the first couple of months of this year-long time scale, structures are starting to form, and astronomy is the only science that's really going on, astronomy and physics, of course. In May of that calendar year, our galaxy finally gets to a shape that we would be able to recognize. We can call it fully formed at that point. Several more years pass by where new stars and planets are formed, and eventually our solar system forms in September of that crushed down calendar year. Life on Earth begins, and finally we can get some other sciences going on. Biology, certainly chemistry was happening this whole time, but really astronomy was the key science in all of those previous months. Then October, our initial atmosphere on Earth didn't have oxygen, the thing that we need to breathe right now. By October of this crushed down timeline, we get that oxygen and things really start to change from there. In November, we get complex life. We open up December a little bit because a lot more things happen in that time scale. We get backboned animals, we get land plants, dinosaurs show up on Christmas, mammals show up the day after in this crushed down timeline. December 30th, dinosaurs become extinct. They didn't have a very long time here. And 10 seconds before the striking of midnight on December 31st, that's really when we start to get modern civilization. Humans have not been around in the universe for very long. So having a sense of what astronomy covers, all of these previous months in this timeline that has been crushed down into a year, all of that is part of astronomy too. So a vast range of size scales and a vast range of time scales. The last thing I'll leave you with in this very first video is that the reason you're taking this class may be because you're really interested in astronomy, and if so, I look forward to lots of discussions, but it's probably because you have to take a science course for whatever degree you're seeking or whatever program that you're working on. The reason that science is a required course, even at the college level, is because it's one of the few ways that we can really practice and build up critical thinking as sort of a target for that whole course. So that's really what we're focusing on in this class, is teaching us how to approach new ideas and how to think through things and how to connect different topics together. And so we'll try to really focus on that in this semester. And along the way, we'll learn a lot of really cool astronomy. But I know that the reason that you're taking this class is not to go on to become an astronomer, although you're certainly welcome to. But we will want to be developing those critical thinking skills through these different pause and think questions, through the discussions that we're going to have in the forums, and through the different activities that we're going to be doing and different assignments that we'll have. I hope that you really enjoy this very first video, and things will continue on from here. But that really is our introduction, chapter 1 of what astronomy is and what we're going to be doing this whole semester.